All right, we're doing 3.7 today, implicit differentiation. And for those of you that like just computation kinds of problems, this is your section. It does take a little bit of practice, but eventually it's not too bad. So what is implicit differentiation? Well, up until now you've been solving derivatives for equations that are y in terms of x. In other words, it's been y equals and then something with x's on the other side. So when it's implicit, that means that the x's and the y's are on both sides of the equation, or at least the x and y are on the same side of the equation as each other. So if I go ahead and kind of show an example, well, actually, let me flip ahead for a second. So an equation like this, 2y plus x equals 3, x and y are on the same side of the equation. This one you could actually do either way. You could solve it for y in terms of x and then take the derivative like normal. Or instead, you could do it implicitly. And I know I haven't gone through that yet. Sometimes, just kind of looking ahead, here's an equation where you have a y in one term and a y squared in a different term. There's actually no way that we could get the y by itself to get y in terms of x on this problem, so you have to do it implicitly. Okay, let's go back to the start because I'm kind of getting ahead of myself. So when I look at this slide, basically what you need to remember is that in the past when you were taking the derivative of y, we usually called it y prime. You can also call it dy over dx. And then when you're taking the derivative of x, we usually call that 1, which is the same thing as dx dx. Now, when you're looking at this notation where you're writing it as a fraction, the variable that you're taking the derivative with respect to is the bottom part, d of x most of the time. And the variable on the top is the variable that you're taking the derivative of in that particular term. I'll have to kind of go through some examples to make sure that's clear. So for example here, y equals x cubed. This is one, you know the derivative is 3x squared with power rule, no big deal. But just kind of thinking of it with this notation, with a d something over d something, derivative of y, instead of calling it y prime, we could say dy dx. That's the derivative of y, thinking of it in respect to x, or with respect to x. And over here we would have 3x squared, and believe it or not, you would apply chain rule. The derivative of x is 1, or dx dx, and so of course you get just 3x squared. This chain rule part, which normally when we first start off derivatives we don't even bother talking about, and then later you learn chain rule, but really it is 3x squared times the derivative of x, and the derivative of x is dx dx, which is 1. Okay, so here's this one where I said you could solve it two ways. If you wanted, if you don't want to do anything new, you could just take this equation and rewrite it algebraically, transform it to get the y by itself and all of the other x terms on the other side of the equation. So if I did that, or kind of rewrote it again, it's just a line, and my slope of the line is -1/2, or you could think of it as derivative of y is dy dx. Derivative of this term is just -1/2. Derivative of 3/2 is 0. So there it is. But if you don't want to do it by simplifying it to get the y by itself first, if you want to try doing it term by term, just doing it implicitly, the derivative of 2y. Okay, well we said the derivative of y is dy dx. So I have 2 coefficient and then dy dx plus, we said the derivative of x is dx dx, which is really just 1. And then over here, the 3, the derivative is 0. So I end up getting this equation here. And then, of course, dx dx is 1, and so I simplify it, and I've got my answer for the derivative, dy dx. So now we come to a problem where you really can't algebraically get the y by itself because y is appearing in two different terms with different powers. You're just kind of stuck with it. So you have to do it implicitly. So if the term, I'm going to go term by term taking the derivative, this first term doesn't have any y's in it. So it's just the same as it's always been. Your answer for this derivative right here is just going to be 10x. I put 10x dx dx just to kind of remind us the chain rule, but of course dx dx is 1, so that first term derivative 10x. Second part over here, this 2 that's out in front, I would suggest you just leave it out in front. And then what you have here is a product rule because you have a variable and a variable being multiplied. X squared is being multiplied by y. So my product rule, I have the first thing, x squared, derivative of y, dy dx, plus the second thing, y, derivative of the first thing, derivative of x squared is 2x dx dx. And again, you don't have to put the dx dx because it's just 1. And then over here, derivative of y squared, think power rule, 2 comes down, y to the first, derivative of y, dy dx. Do you see how I'm putting these dx's earlier? That's just so that when you get to this one and you think, oh, derivative of y, you don't think it's 1. It's dy dx. Derivative of y is dy dx. Equals derivative of 8, don't forget, 0. I guess one thing, if you wanted to try to just kind of get a handle on this right away, the terms that don't have any y's in them, you just take the derivative like normal. This is 10x. The terms that have the y's in them, make sure that when you're taking the derivative of it, you're adding a dy dx in there. It's due to chain rule, but make sure every term, whenever you're taking the derivative of a y, you put in a dy dx. Okay, the rest of it's just algebra. I distributed my 2 in here, and then I saw I had dy dx appearing twice, so I pulled that out in front, factored it out, and just kind of solved it through. Simplified by dividing through by 2 on top and bottom at the last step. Okay, what if they say find the slope of the tangent line to the graph at this point, 2, 3? And we're going to assume this is still looking at this previous example. So I've already gone through, I figured out the derivative. Derivative is slope. And here it is, my derivative in terms of x and y. So if I have a particular point xy that I'm interested in finding the slope out, I just need to plug in the xy coordinates. So that's what I'm going to do. So here's my slope equation. X is 2, y is 3. Plug those in, and I get my answer. Nice and simple. Okay, what about this one? Here it's asking for the second derivative. The x's and the y's are not on the same side of the equation for this one, but we usually have y equals, not cosine of y equals. This one has x in terms of y. So I'm just going to leave it alone. I'll take the derivative of each term, thinking of it implicitly, remembering that when I take the derivative of y, it's dy dx, and when I take the derivative of x, it's dx dx. So derivative of cosine is negative sine y times the derivative of y. That's the chain rule part. I have to remember to take the derivative of the angle. Equals, and over here on this side, the derivative of x is just 1. You can say 1 dx dx. On the next line, of course, dx dx simplifies to 1, and I solve and I get my answer. So that's my answer for my first derivative, I should say. Comes out negative cosecant y. But remember, we were asked for second derivative, so we're not done. Now that I've got the first derivative, dy dx, all by itself, I go ahead and take the second derivative. And on this side, derivative of cosecant is negative cosecant cotangent, but it's already negative, so it becomes positive. And then, of course, the derivative of the angle. The angle is y. The derivative of that is dy dx. Now, you would think that maybe you're done, but no, you're not. This dy dx right here, we want to substitute out the dy dx with negative cosecant y. So when you're doing a second derivative, chances are the dy dx first derivative is going to be in the problem somewhere, and you're going to have to go up here and go, oh, I can substitute that out. Now you have an equation that doesn't, for the second derivative, that's not in terms of the first derivative, which is what we would like. Okay, simplify, you've got. So this one is find y prime, that means first derivative. So I'm going to go term by term. Derivative of x is just 1. You can say 1 dx dx, but of course it's just 1. Derivative of sine y would be positive cosine y times the derivative of y, which is dy dx. Okay. On the other side, you have a product. You do product rule. Product of variables, right? Whenever you have a variable being multiplied by another variable, it's product rule. So first, x, derivative of second, derivative of y, dy dx, plus the second thing, y, times the derivative of the first thing, derivative of x, of course, it's just 1. Dx dx are just 1. At that point, I clean it up by dropping these dx dx's. Those are just 1. And then I want to get the dy dx's on the same side of the equation, factor it out, put the terms without the dy dx on the other side, and get my answer. Okay. So here I put in 3 practice problems. As always, go ahead and hit pause, give them a try, and when you're ready to see the solutions, hit play again, and I'll go through them. Okay, so the first one, find the derivative. So looking at it, the derivative of the first term, power rule, 2 comes down, that's 10y to the first, times the derivative of y. Oh, I just wrote the equation down again. Okay, so 10y to the first, derivative of y, plus, and then the derivative of sine is cosine y, but don't forget chain rule, derivative of the angle, dy dx. And over here, x squared, derivative just 2x. dx dx. The dy dx's can be pulled out, and I can solve, get my answer. Okay, the second one, find the slope of the tangent line at 4, 0 to the graph of this equation. Okay, slope of the tangent line, that's the derivative. And then once I get the derivative, I need to plug in the point 4 for x and 0 for y, and I should get my slope at that particular point. Okay, so here's my equation again. Taking the derivative of the first term, this will be a 28y to the third dy dx. Again, that's power rule. 4 comes down, 4 times 7, y to the third, derivative of y. This one in the middle, that's product rule. I have x cubed, derivative of the second term, plus the second term, derivative of the first term. And then finally, I have x, derivative of x is 1, and equals derivative of 4 is 0. I go ahead and pull dy dx out of the terms that have it in it and solve. I get this equation. This will represent the slope of this fourth degree polynomial. This is the slope of that fourth degree polynomial at any point. I'm interested in the slope at the point 4, 0. So I go ahead and plug in 4 for x and 0 for y, and I got my answer. Okay, last one. Find the derivative of this equation. Now notice we want the derivative of y, but with respect to x. And here in the problem, there are no x's. So every time I take the derivative of y, remember it's dy dx. And this time when I take the derivative of t, it will be dt dx. If I were to have an a in there, it'd be dA dx. The only thing that turns out to equal 1 would be if I had an x and I was taking its derivative, which would be dx dx, but there are no x's in there. Now they do give me something that I'm going to need to substitute out dx dt before I'm done with the problem, so I'll just kind of put this fact aside, come back to it in a little bit. So my first term right here, the 2 I'm going to leave out in front, and then this is a product of variables. I have a y cubed and I have a t. So product rule. First thing y cubed, derivative of the second thing, dt dx, because we're taking it with respect to x, plus the second term t, derivative of the first term, 3y squared chain rule dy dx, plus, and then over here, product rule again, so I have t cubed, derivative of y dy dx, plus the second thing y, derivative of the first thing, derivative of t cubed is 3t squared, chain rule dt dx. On the other side of the equation is a 1, the derivative of 1 is 0. Okay, so I went ahead and distributed the 2 that's out here in, and took off all the parentheses. And then I noticed I have 2 terms with dy dx in them, so I factored that out of those 2. And the dx dt's, I have 2 terms there. I pulled that out, and I basically got this equation. I could go ahead and divide through to get the dy dx by itself if I wanted. I first chose to come back to this fact and see that dt dx is defined to be 1 over cosine t. So I plugged that in, and then I went ahead and get dy dx by itself. So I've got my derivative in terms of y and t. Okay, that was it. Thank you so much.